Sure. It's important to know, probably not for exam 2, but for just in general, again, for final exam. You just need to know this, okay? So plus, left, and leading. Okay, remember one direction. I'm not expecting you to remember both, but remember one direction so you know the other one, okay? Plus, left, leading. How do I understand this? Cosine omega t plus theta, okay? So the time domain signal plus theta. What's happening? It's moving to where? Left. I told you already. Left. So cosine wave, like this. Okay, moving to the left. So it's leading. And the polar, just draw this angle in the polar domain. Plus means what? This. Right? So if you rotate in that direction, it is moving the signal, the time domain signal, to the right or to the left? To the left. Plus left leading. Unfortunately, lagging has the same letter L, so I don't want to directly just tell you PLL, which is the phase lock loop, which is a component in electronics engineering. But don't want to just tell you this. Plus left leading, okay? Plus left leading. So it's going to be minus right and what? Lagging. So don't remember that, just remember this at least, okay? So from here to here, moving to the left, how much degrees is needed from here to reach here by moving it to the left? Pi, right? Yeah. It's a very, very bad problem because you rotate either direction, you'll get the same answer. Anyway, but you know how to do it, right? So it's plus left leading, yeah? And now let's look at the in-class exercise problem set here. This 3 pages one I didn't bring it over, so I have to open up a hard copy, a PDF version here. The hard copy is just 1 page, just 2 problems. I have another hard copy, have more problems in there. Let me see. You need to know both, okay? I have it here. This one. All right. That's the right one. First, I'll do this. It's not on this page. I just took out 2 problems from the problem set over here. Since you don't have enough time to run through everything, but these ones are also the ones you need to know. Okay, since I sent it through Canvas, but no one opened it up, right? I know. Could you pick up your in-class exercise for the ones just came in? Just feel free to come over and pick it up. Okay, I'm putting this here. What's overall inductance? L3 in parallel with L4, right? Or 1 over just in case. because it's 20 points. So 1 over L3 plus 1 over L4, right?
Yes.
For the second one, L1 plus L2. For the third one, 1 over C1 plus 1 over C2. For the last one, C3 plus C4. Make sense? No question on this, right? Don't lose points on this. It's so simple. Just it's a gift. Thanksgiving gift. 20 points, right? It's gonna be more complicated than this one, but if you know how to calculate the power line series inductors and capacitors, you should be able to do it. Next. Oh, sorry, it's too small. Let me zoom in. The op-amp in the circuit. Again, this is homework problem. Okay, it's not an exam problem. There's no way that I can give you the exam problem, and I don't want to do that as well. So this is a homework assignment problem. You need to know op-amps. The op-amp in the circuit is ideal. Okay. Is this a comparator or an op-amp? Op-amp or comparator? What to look at? Negative feedback. So there's a negative feedback. So it's not a comparator. It's a. So what is it? Yeah, op-amp. But what type of configuration? Can you tell? Look at the signal, right? So where the signal is connected to? Doesn't matter if I have 2, 3, 5. Doesn't matter. But where the signal come from, or connected to? The non-inverting terminal, right? Non-inverting, see the plus sign. So this is called what? Non-inverting configuration, or non-inverting op-amp. Non-inverting. This is inverting. If the signal is connected to the inverting terminal, it's called the inverting op-amp, right? Okay. So if you have a non-inverting version of it and have multiple signals connected to the same point, and this is called what? Summing. Non-inverting and summing, right? Okay? If you have both terminals have signal inputs, you have signals connected to both terminals.
Difference.
Yeah? A typical difference amplifier looks like this. R2, R1 is symmetrical, so you can keep the noise at the lower level. So it's going to be labeled as what usually? As a convention. It's not part of the exam or part of the test, but just let you guys, I'm just curious to see if you know that. What's the naming conventions for the terminals like this? It's a VM, VP, right? Oh, VM. Or there's a negative and positive. Or sometimes you see VM and VP, it's minus and plus. But now let's just assume it's a VM, VP. VN is negative terminal. VP is the positive terminal. I have two voltages, and each terminal has a voltage source connected to it. And this becomes a difference amplifier. We didn't derive the voltage gain of it since we didn't have time. But you need to know that it's symmetrical. R2 over R1. I labeled the same name because I'm assuming they are the same values. And V out equals VP minus VN times R2 over R1. Okay? So that's the right way to do it. That's the right way to use this difference amplifier. Sometimes you can see the name could be differential amplifier, but it's the same thing. Differential amplifier. They use these two names interchangeably. It's the same stuff. All right. If I remove this resistor, if I remove it, definitely it's not going to perform as good as the traditional configuration. But since we still have signals in the two terminals, what's the name of this amplifier though? What's the name of it? What's the configuration? If I remove this resistor, is it good? It's not. It's just a regular amplifier. It won't reject a lot of noises. We didn't drive the equation about how it rejects the noise. But just let you know, you got this symmetrical configuration, it's going to reach the best performance. But now if I remove this resistor, it's fine. It's going to still amplify the difference. Okay? Because we have signal in both terminals, it is still called a difference amplifier. It's still called a difference amplifier. Just let you know, even though it's not perfect. Okay? This kind of thing exists in the textbook on the paper. Okay? Not going to be used. Anyway, you got two signals in the two terminals. It's going to be a difference amplifier because it's amplifying differences. Right? Okay, let's come back to this problem set. So this guy doesn't have another source over here, so it's basically just a non-inverting terminal, a non-inverting configuration, and it's a summing amplifier. Okay? How do you derive the voltage gain for this guy? Let me ask you one very simple question here. Do you have current here in this branch? No. Keep in mind, no current, okay? It's a high impedance, very high input resistance. Current is not getting into it. So what is this doing is you have two sources and they are being superimposed to this terminal. Okay? So it's showing a voltage here, and because it's negative feedback and it's the ideal op amp, so this voltage will be measured to this point. So before we moving forward, if this is given like Vs, I don't know what the voltage is, for example 1 volts. Let's just extract this circuit. I know someone still don't know how to do it. Just look at this part, okay? Let's say 1 volt, 4 volts, 10K, 12K. Can you calculate the voltage here? Yeah, that's the simplest circuit you can get, right? Just two sources and two. So these are shorted together because they are both grounded. So eventually, it's just two sources, two resistors. You can use either mesh, KVL, no voltage method, whatever. So this is easy to get, right? So if you get that voltage here, and you know the voltage is being measured to this point, can you calculate V out from that point? What's the voltage here? 0, grounded, right? It's 0 volts. And then the voltage here, no current getting into the op amp, so no current over here. So basically the current flows from here, go up, and reach VL. Okay? So VL is over here, so basically it's whatever is the voltage you calculate from here, minus VL over 40K equals 0 minus this voltage divided by 10K. Let's assume this is Vx, okay, Vx. You can calculate Vx. And so it's going to be 0 minus Vx over 10K, which is a current over here. It's going to go up. So that current is 0 minus V out over 40K. That's it. That's the equation. Determines V out. Any question on this?
Minus VL.
Thank you. Any question on this? No? Move to the next. What about this one? You have done this, right? When you did the homework assignment. Homework 7, I think. Part of your nightmare. comparator or whatever, just let me know. What's the configuration? Yeah? Yeah? Wait, nope. Oh yeah, Let's say just a summing amplifier, okay? A summing, and eventually it's doing a differential as well. But let's just say some. And actually, it's not a really legit question. You know what? The thing is, even though we don't have a source here, but it's 0 volts, right? It's actually using this voltage minus 0. It's still a differential amplifier. The only thing is we don't use it as the traditional differential amplifier like this. So in my knowledge, I either just use a very simple amplifier configuration. You ground the other point and just use it as a low quality whatever non-inverting or inverting amplifier. Just make it simple, right? You don't have to consider the trace length to make it symmetrical. Just directly throw it into the circuit, it's going to work if you don't quite care about the quality of the signals. So these are just called non-inverting and inverting, okay? If you care about the quality of the signals and low noise, you just use a differential amplifier. But you have to keep this one over here to make it rejecting noises. It's only 2 choices. You don't have other choices, actually. But sometimes in the textbook, in the exam, somewhere else, you'll see this is gone, but you still have 2 signals. So they expect you to say that, to identify this is still a differential amplifier. Just let you guys know, okay? Just let you guys know. So this is a non-inverting amplifier, and this guy is a summing amplifier because you have so many signals summing to the same point. Do you need to do a KCL on this wire? Let's take a look. That one, you got a 1 resistor, 1 resistor, 1 resistor, resistor, R1, R2, R3, R4, ground, V1, V2, V3. So how do you approach this problem? VD, because it's an ideal amplifier and it has a negative feedback. Oh, another thing. So plus minus 12 volts, does that make sense to you guys? It's a dual power supply, right? This is what we usually do in the lab or in the textbook. So we don't use ground, but usually in the real world we use a ground. So in that case, you have to add a DC offset. But I think it makes sense because you don't want to confuse the beginners too much. So we are getting rid of the DC offset, not lifting the signal to 50% of the voltage range. But instead, we just let the signal swing around 0 volts. So that's something we don't have to worry about. I know it's complicated, but we don't worry about that. We just use it because eventually it's a dual power supply and the signal will swing around 0. So we don't worry about the lifting the signal, DC voltage, like high pass filters, low pass filters, all these kind of things. It's easier, making things easier, okay? So AC signal will just swing around 0 because that's the middle point of the op-amp. So we don't worry about the power supply, plus minus 12 volts. And this DC voltage will be measured here, right? So eventually you have V1, V or VA, VB, VC minus this point and get the 3 currents as it merges to the same point to get a 1 main current. That current flows through here and across the RF. Okay? Any question on this? Work on it if you still have questions after class. Make sure you can do it. Another one is something that we didn't practice in class. If you don't pay attention, you will lose points on this, all right? It's a trap. It's a trap. Look at this. VT is given. VT is given. Can you find out IT? Can you plot IT for me? It's on your paper. Just start working on it. I'll give you 2 minutes to work on it. Oh, the answer is given on the paper, but try to not looking at it and plot it somewhere else. What's the equation dominating this behavior here? C dv dt, right? C dv dt. So these are linear curves. So dv dt is a constant. So if you look at this from, it's 2 minus 1 is 3 difference. Over here is a 3. And 3 as well. So it's basically 1, right? So the slope is 1. C dv dt, you are getting a 1 here. Getting a 1 here. So what is, so 1 times 500 microfarads is giving you 500, what? Microamps, right? So for the first part, you are getting a DC current of 500 microamps. So from 0 to 3, it's just a bar, 500 microamps on the top. It's positive current on the top. What about after?
The slope is 0, so you've got
No current. So keep in mind, for current, it doesn't stay, okay? It doesn't stay. Voltage stays for capacitors. Current doesn't stay. So there's no current. But voltage stays. It's a static voltage. So the voltage is not changing. Just look at this equation here. dV dt, right? You got a voltage changes over time, then you got a current. Okay? If you don't have voltage changes over time, you don't have current. Okay? You wonder why? It's just a product. You buy a product, you read the user manual, right? This is a user manual. Tell you voltage doesn't change, no current. It tells you that. They designed that way. Just use it, right? Just use it. It's a user manual. Read the user manual, that's how you use it. So if there's no voltage change over time, same voltage, DC voltage, no current. Current drops to 0. And then you got a current changes to the negative domain. So the slope here is what? 2 over what? 5, right? So it could be negative 2 over 5, which is negative 0.4. So negative 0.4 times 500 microfarads is giving you this much microamps, right? So that's the DC current. What's that?
Would it be 1 over 5? Maybe 1 over 5? Because it's 2 minus 1.
Oh, yeah, yeah. So minus 100 microamps, right? Yeah, so it's going to be a bar at minus 100 microamps for currents. Okay, so now try to plot this from that current curve. No idea? Think about it. Yes, that's right. Try it. We'll go through that later. I'll give you 2 minutes to work on it. Okay? Forget about this, right? How do you forget about that? Just forget about that. Assume you only have this guy. That's the only thing you know, okay? How do you recover it back? Have to know how to do it. How? IT equals C dV T dt BT equals 1 over C 0 T IT dt. Okay? What is given? I. What is asking for? V. What is C? 500 microfarads. So 1 over C is what? Which is $2K. Here to here, 0.5 milliamps, 0.5 milliamps. So 0.5 milliamps equals 0.0005 amps, right? Okay? And it's a constant, it's constant. Do you know how to integrate constants?
Yes.
What's the time domain?
0 to t.
Right? 2K. 3. So this is what? This is the voltage after, right?
It's a change in voltage.
The change of the voltage, yes. What's the initial voltage? It's 0. So what's the final voltage?
3.
Okay, it's 3 volts, right? 3 volts. Oh, there's a -1 as a initial voltage. Yeah. So initial voltage is -1. So see. So changes of the voltage is 3 volts, so are eventually getting 2 volts, right? And it must be a linear curve because that's how we integrate it. It's just something times t, right? That's how that works. So in that case, you need to add what? To complete the equation.
Got it. Thanks.
Here, 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 and here, and here. Okay? If I give you this, all these parameters here, and I give you this, you should be able to plot it, right? It's linear, you know the difference, you know where to start it, get started, and you know how to plot it. All right. Next, natural response. Natural response. Let's look at the one on your in-class exercise first. What's what we have over here? I think I have the same copy here as well. Let's go through that one first. This guy. This guy. So switch has been at A for a long time. So what's the voltage over? What's the initial voltage across C? VG is a DC voltage, 54 volts. 54 volts. R1 is 44K. 54 volts. R2 is 16K. C is 65 microfarads. How to calculate the V0, VC0, VC0? Is the voltage the same as the voltage across the resistor? Yes. So what is the voltage here though? DC voltage, okay? DC voltage. It's been there, so the switch has been here for 100 years, so there's no current.
Isn't it shorting at 16?
It's not shorting, it's disconnecting. This is gone.
Close to 0.
Zero current. Pass.
Oh, zero current, but you have voltage, right? What is VC0? It's just voltage divider, 54 times 16K over 44K plus 16K, right? Hmm? What about VCT when t is larger than 0? Or sometimes you will see VC0 plus. VC, no. Oh yeah, what is a VC0 plus though? What is a VC0 plus? Same. Why? Because VC0 plus equals what? VC0 what? Minus. Because capacitor, the voltage is across the capacitor cannot change instantaneously. You need an infinite amount of current to change it instantaneously. It's a bucket of water, right? How can you just make a zero amount of time to get rid of the water in the bucket? Is that possible? You gotta pump it out, use a pipe, right? It takes time. Unless you're a magician. Make sense? Okay. So whenever this switch is here, if this switch is, you switch the switch to B, okay? Is VG still engaging? Or still engaged or no? No, it's disconnected. So what's the remaining circuit left? Is this correct? Mm-hmm. Exactly. So we always model the reference currents flow into the cap. Okay? So you are wondering like, hey, you said it's discharging across the resistor, but you put a reference of the current flow into the cap. Does that matter? It's sucking current into the capacitor. It's just a reference, right? So it's gonna draw current from ground. It's gonna do this, right? That's how we model it. It's also discharging. It's also discharging across the resistor. Doesn't matter. You don't worry about all the directions. Okay, it's doing this. Okay, doing this. What is VT? What's so first, what is the equivalent resistance for this discharging circuit? R2 plus R1, R2 times R1, oh no, R2 times R3, R2 plus R3, R2 divided by R3. Just kidding. What is the equivalent resistance? Parallel circuits, right? So RTH equals R2 in parallel with R3. What's next? Find a tau. What is tau? RC is RTH times what? C. What is C? Capacitance. Just the capacitance is not changing, okay? Okay? So find out tau. And then VT equals what? Natural response, right? What's the equation for natural response? The easiest problem you can get from homework 8, I think. Right? So the initial voltage times the attenuation factor here. Any question on this? Similar to inductors, right? So what's the inductor's tau? Okay, same. But for all the rest is just the same equations. But using i's, right? So ILT is what? IL0 times e to the minus t over L over R, right? That's the only difference. Other than that, it's all the same. Now let's look at a inductor problem. Oh, before doing inductor problem, let's do this first. Right. So first step, convert sine to cosine because we don't like sines. We use the reference of the cosine signals. So this equals 3 times cosine. It won't change. It's going to be all the same in the future. Just directly, it's no-brainer. Just directly minus 90 degrees. So sine anything equals cosine anything minus 90 degrees. Oh, t. Sorry. Then start from there. Okay. So this is also what? This is 15 angle, 53.13 degrees, and this is what? This is 3 as amplitude and 90 minus 90 degrees, right? Polar form. So first step, convert these ones to its impedance form. So J omega L is J times omega, which is 5,000, times 400 times 10 to the negative 6. And that becomes 2J. Okay, and for capacitors, it's 1 over J omega C, which is minus J over omega C, which is minus J over 5,000 times C, which is 50 times 10 to the negative 6. And eventually we're getting 0.4 times 10 to the second. So it becomes 40 minus 40J. Is that correct? So disregard all the inductance and capacitance. Directly convert it to its impedance. And then just use the impedance as a resistor and use the common circuit laws and theories you have learned in the beginning of the semester. Treat them as resistors. Never think about time domain. Only deal with phase and amplitude. You are going to have a problem like this in the exam. Okay, just make sure you can do it. Never think about time. Eventually, you get all the phase and amplitudes, and eventually you want to get a final answer. Then you write down the time domain stuff. Otherwise, you never deal with the time domain things. Never think about it. It's all treating every single component as a resistor, but using the impedance instead of the resistance. That's it. Make sense? You have a question or no? No? So you can use 2 different methods to solve a problem like this. I have learned 2 mainly, but you can also do superposition, but I don't recommend it. But for the 2 methods you can use, the first one is called node voltage method, and the second one is called mesh current method, right? You can use either one. The pain is pretty much equivalent. It's a lot of calculations. No difference. Just pick up one, okay? What's the node voltage method? VG1 over 2J. That's the current going into it. And from the other side, VG2, you have to put a minus sign in front of it, right? So this becomes minus 3 minus 90 degrees minus Vx over minus 40J is the current going in here. 2 currents going in, 1 current going out. So this equals Vx over 6. That's it. Okay? List equation is very simple, but calculation takes time. Just be patient. I think I went through this in the recorded video, right? Uploaded video. So what about mesh current method? I1, I2. Okay? You could start from here. You can list it in either way. If you follow my method, it's going to work, right? Or you can put VG1 on one side of the equation and place all the voltage drops on the other side of the equation. It's still the same. I'm keeping everything on the same side of the equation, which is fine, okay? Minus VG1. VG1 is 15. Plus I1 times 2J plus I1 minus I2, 6 ohms equals 0. If starting from here, you're getting I2 minus I1 times 6 plus I2 times minus 40j minus VG2, right? Minus VG2. This is VG2 minus two equations. If your calculator can do polar form calculations, I recommend using the polar form for all the parameters. Otherwise, you can just use the rectangular form as well. It's going to give you the same results. Damn, I still have 6 minutes. So I'm going to run it. Okay, let's do one of them really quick and see how much we can get. Let's use this one, okay? BG1, 15, 53.13 minus Vx over 2j plus minus 3, no, 40j How do you want to start from here? I want to start.
Set it equal to 0.
Yeah, if you convert these to polar, so you can do the division, get rid of one of them at least, right? I don't know if it's easier or not, but let's just do it. So what is 2j? J is here, right? That's the imaginary, that's the real domain. So j, because there's no real part, 0 plus 2j, and this is 0 minus 40j. So basically 2j is over here. This is minus 40j, okay? Right? Okay. So basically this becomes 53.13 minus Vx over what? To what? 90 plus minus 3 minus 90 minus Vx over what? 40 times what? Minus 90 equals Vx over 6, right? And then you can do this. Keep in mind, polar form division is the easiest way you can do, okay? It's, if you see a division with a polar form, you should feel pretty happy because it's super easy to do. That's the whole point. That's why we convert everything to phasors. So when you are doing a multiplication and division, use the phasor form, super simple. For example, this one, okay? So we can change this one to what? To 15 over 2 minus okay? So this is so simple. Real divided by real, 7.5, and angle minus angle, keep in mind. Because this is what? This is actually 15 this, right? So division for the e is exponential is getting minus on the top. So that's why this is 53.13 minus 90, which is 36.87. Yeah? Minus, you can do this one more time here, divide this by this. No, you can calculate it, right? Hmm?
Isn't there a negative in front of that 40 on that term?
No, because it's negative, yeah, you can take out this,
Oh, okay.
yeah, same thing. Okay? But anyway, so the angle is gone, right? That's a good part of it. 0 degrees. Pulls everything to the real domain. Real number only. So this becomes what? Minus 3 over 40, right? And minus Vx over 40. Okay, so you just combine the terms with Vx together and move other things to the other side of the equation so you can find out Vx easily. You don't have to use this method, but this is the one I prefer because you can use a calculator eventually to do the polar summation and subtraction. If I tell you this, 3 angle 45 plus 5 angle 50, can I calculate this by hand? It's not that easy to do. Use a calculator. So when you do the phasors, you prefer division and multiplications. If you see a summation of the phasors, if you just have to do it, you can still do it. Why? Because this equals what? 3ej45 plus 5ej50, right? And use Euler's equation. This becomes 3 cosine 45 plus j sine 45 plus 5 cosine 50 plus j sine 50. And now I can definitely calculate these ones. So eventually you convert it to the rectangular form, and eventually you add the real parts and imaginary parts separately. You're getting like a plus bj, which is still fine. From a plus bj, okay, you can also convert it back, which becomes a squared plus b squared and ej what? Arc tangent b over a, right? Or this also equals a squared plus b squared what? Angle of what? Arc tangent b over a. That's how you do things back and forth, okay? See you on Monday. Oh, you want to turn it in, right? You want to turn it in? I want to give you the feedback. Did you finish it? I just take it back home. It's okay. I need a better weekend as well.